To introduce the speaker, Xinnan D, who is for the Kavli Institute for Particle Astrophysics and Cosmology. This is a sponsored talk with collaboration from NASA, the Kavli Institute, also the NASA Community College Network. And really that's to bring science experts into the community colleges for students to talk to professionals and know people that are doing current research. And I would also like to thank, and this is who sponsored the talk, the American Astronomical Society. And I did want to give a big introduction to her about her career path, her degrees. However, that's part of her talk today. So, oh, and we have that beautiful poster. So, does anybody know what that's the image of? Yes. That is the Orion Nebula, right? And actually in the far left corner, they call that the Running Man Nebula. Does everybody see that? No. So this is going to be our speaker today from Stanford University, Outreach and Engagement Manager for HIPEC. I'd like everybody to welcome our speaker, Xinnan D.
All right, thank you very much, Dan, for that very nice introduction. Because yeah, we discussed at dinner, and I say, hey, part of my talk is actually going to be my bio, so shh, yeah, don't say too much. So thank you, and it is my absolute pleasure to be here tonight. This is actually my first time visiting the Central Valley, and I'm just so excited to see all of you here. Dan previously told me, oh, don't be scared. We might have a full house. I mean, now I see that he wasn't kidding. But yeah, so great to see you here. And in the next hour or so, I am going to not only present what I have been doing in terms of research, but also trying to share a little bit of what kind of decisions or intersections that I have actually encountered to get to where I am right now. So as Dan mentioned, I am currently working at the Kavli Institute for Particle Astrophysics and Cosmology, or short, KIPAC for short. And that is an Astro Research Institute co-managed by Stanford and SLAC. And I joined this position about almost 3 years ago, and I am now the outreach person in the institute. So, oh, and I apologize. Whenever you see something like this, it's just a bullet point. There were some conversion errors, so you're not missing anything essential. So a little bit about myself. I did my K through 12 education in Beijing, China, where I was born and raised. I went to Nanjing University to get my undergrad degree in astronomy, and that was all because I was very inspired by one book by Stephen Hawking, A Brief History of Time. And I believe this was exactly the version that I read when I was in high school. It was an illustrated version here, and I almost did not understand a thing in there. But I enjoyed the illustration, and I thought they were really cool. At the time, I was also pretty good at physics. So after a couple years, I was like, maybe I will just give astronomy a try in college. At least that's something that I would like to spend some time on. So that was initially how I decided on majoring in astronomy. And Nanjing University was, and still is, the top astronomy program, at least in undergrad, in China. So that's where I went a little bit far away from hometown. And after getting my bachelor's degree, I did my PhD, master's and PhD at UCLA, after which I moved to UC Riverside to continue my postdoctoral research work, where I also got more experience in managing education and outreach programs there, and I'll talk more about that. And about 3 years ago, I finally moved to the Bay Area for my current job, which is completely education and outreach focused. So, a little bit about why I chose to do grad school and why I chose to do research. I think there was kind of a long period of realization before I made the decision. So when I first started in college, maybe after a couple of years, taking math, physics, and astronomy courses, I finally got a chance as a sophomore to do a small research project. So that one was very theoretical, heavy in math and physics. And I remember one of the first tasks I was given was just to finish reading a 50-page paper that revealed the entire topic that I was going to work on. And after a semester, I couldn't even finish a third of that because I always got stuck in deriving the equations that I did not even understand. And I feel like, wow, that was just, it was like this gigantic block in front of me because I hadn't even learned that much advanced physics and astronomy to do any of that. So that kind of like shut the door for me to do anything theoretical afterwards. And then at the summer of my junior year, I had a chance to actually go to UCLA to do a 10-week summer internship. And that's where I discovered my passion or my like for galaxies. So what I was doing was basically analyzing images of galaxies almost exactly like this way. And even that's just single colored, it gives me goosebumps when I'm seeing them. And I just found myself, enjoying doing the tedious work even when they seem to be repetitive. So after those 10 weeks, I was like, wow, okay, well, I just enjoy doing all this Excel spreadsheet. Now I know not to do. But after that, I was like, okay, well, maybe I can spend a little bit more time on galaxies and on astronomy. And that's how I went onto this research route, and that finally got me into doing extragalactic astronomy. So a little bit about my research, and we're going to introduce some of the terms here, and I have to give a heads up that astronomers always use very confusing terms, so I'll try my best to explain them well. So I basically study the gas in very distant galaxies, and I use a spectra to get their physical properties, including chemical composition, including their how they move or their kinematics. And so to be more specific, I studied the gas that is in between stars, what we call the interstellar medium, and also kind of in the outskirts of the galaxy, that's what we call the circumgalactic medium. So all those are components of a galaxy. And tonight, we're actually going to explore a little bit about how these components all come together and what is the significance of actually studying the gas. So now there's a question for you. Whenever you think about a galaxy or you talk about a galaxy, what things do you think are there in a galaxy? Stars? Yes? Yes, a lot of gases. Good guess. Black hole. I heard black hole somewhere. Yeah, anything else? Planets. Great guess. Anything else? Yeah, louder is also fine. There's no wrong answers. Matter, I like that. You're kind of like encompassing everything. Great, yes, so we have stars. We also have groups or clusters of stars, right? Star clusters. Some galaxies, or most galaxies, there's dark matter. Even though they are not emitting any visible light, they're still interacting through gravity. There are black holes. There are also supermassive black holes that sits at the center of almost every single galaxy, including our own Milky Way. And of course, since we're talking about my own research a little bit, there's gas. And gas is what we will be focusing on tonight. So to start with, stars, when we're thinking about them, they actually form in cold and dense clouds that are made of hydrogen molecules. And under small perturbations or instabilities, this cloud would collapse. And due to gravity, it starts to attract more and more gas surrounding it, right? So you'll have this cloud that gets bigger and bigger and heavier. Well, at the center, the temperature is getting higher and higher because gravity is trying to pull everything inward, and it's compressing that gas. So when the center becomes hot enough, and when I talk about hot, it's like really hot, it's about 13 million degrees in Kelvin, and that's 24 million degrees in Fahrenheit. So we're not talking about like pizza oven hot. It's like thousands of times hotter than that. And when it's that hot, hydrogen will start to burn, fusing into helium. And when that happens, we consider that as birth of a star. And here you can actually see the Orion Nebula that you just saw on the poster. So Orion Nebula is one of the most famous star-forming regions that we see in the universe, and also it's very close by, easy to study. So it's in the constellation Orion that we can see typically in the fall around this time and in the winter. And there's also Pillars of Creation. This is a Hubble image, but now we also have the same image, but now from James Webb, in the Eagle Nebula. And these are immense columns of cold hydrogen gas where massive stars are embedded within. So this is also a very prominent star-forming region. And once a star is formed, it spends most of its time, about 90% of the time, being structurally stable, and it also gives out relatively constant output. So there are always two forces when we're talking about a star being stable. One is the inward pulling gravity, and the other one is the outward pushing pressure. So for a star, once it's steadily burning hydrogen at its core, fusing hydrogen into helium, we consider that as the stable stage that we call the main sequence. So 90% of the time, stars spend on the main sequence. And for our sun, the main sequence life, it's about 10 billion years. So our sun has already been burning hydrogen in a very steady rate for about 5 billion years. And there's another 5 billion years to go. So our sun is literally like at its middle age in terms of being stable or being a main sequence star. So what is going to happen after 5 billion years? What's going to happen, to all those like 10% of the star's lifetime? So here I am going to show a video which I believe can explain things better than I would. And this is actually one of the best visuals I actually found on the internet. And I highly encourage everyone, if you are interested, also to check this out. It's developed by NASA.
In this demonstration, you'll use balls of clay to explore how stars fuse elements inside their cores. Each different color represents a different element. Here, pink represents hydrogen, blue is helium, purple is carbon, orange is oxygen, and this tennis ball is neon. We'll start with hydrogen, just like you've got in the center of a young star. The inside of a star is hot and dense, and all of these hydrogen atoms keep bumping together. Often, some of them will stick together. This is called fusion. So we squish together 4 pink balls representing hydrogen, and these form a new element, helium, represented by the blue clay. The sun's been doing this for nearly 5 billion years. Eventually, the hydrogen in the center of the star runs low, and we've mostly got a lot of helium jostling together instead. When hydrogen fusion stops, the star is no longer in equilibrium, and the core shrinks down. But this makes things even hotter, so the star can start to fuse helium into carbon. So we squish together 3 blue helium atoms to make 1 purple carbon atom. In the sun, this is where things will end once the helium runs low. But if a star is much bigger than the sun, the core will shrink again, and it will get even hotter at the center. Now the star can fuse together a carbon and a helium atom, creating oxygen. So we'll squish a blue helium atom and a purple carbon atom, and that turns into 1 orange oxygen atom. You can imagine what happens when carbon runs low and fusion stops once more. The core shrinks, things get hotter, and new fusion can begin again. Helium and oxygen start to fuse into neon. So we squish a blue helium atom and an orange oxygen atom, and swap that out for a tennis ball that represents neon. Depending on the size of the star, this process can continue through the periodic table up to the point where iron is formed. But to fuse iron, you need to input energy. With energy going into fusion instead of coming out of it, the star can never be in equilibrium again, and its days are numbered.
Great. So thanks to that video, it explains a lot of things that I wanted to cover. But basically, you can see that there were multiple stages that a dying star has to go through. And at every stage, it feels some new heavy elements at the core. And when we're talking about heavy elements in astronomy, basically everything that is not hydrogen or helium is called heavy. So yeah, just want to make the distinction there. And if we remember from the video that the fusion inside of a star would stop at iron. However, if we look at all the elements before iron, we see that there's hydrogen and helium, which were mainly there, created very shortly after the Big Bang. Of course, helium, part of that was also created inside of a star, right? Hydrogen fusing into helium. And then for the other elements that we commonly see in everyday life, including carbon, nitrogen, oxygen, or even the nutrients essential to our human bodies, like potassium and calcium, those are mostly, if not exclusively, made inside of a star. And those are where all those elements initially came from, and later on got onto Earth. So what would happen after fusion stops at iron? What happens is, well, once iron is present in the core and there's no more fusion going on, basically there is no outward pushing pressure to fight against gravity. Right? So gravity will win and try to pull everything inward, and the massive star will experience a drastic gravitational collapse. So the core will be compressed into like denser and denser object, and eventually form a neutron star or a black hole. And the other surrounding materials that is typically in the envelope of the star, they will also almost like free falling onto this shrinking core. And once it hits the surface of the core at very high speed, it gets splashed out. So this kind of violent process, once this explosion happens, we call this the supernova explosion. And this supernova explosion can be so energetic that even us, we can observe a supernova explosion that happens in a different galaxy. And I believe there were actually a supernova explosion happened last May, so May 2023, in the Pinwheel Galaxy, that even just with a few minutes of exposure when you're using a telescope, you're able to see it's on one of the spiral arms, and it was not there even just a few weeks before. So those are how energetic those are. And of course, once the supernova explosion happens, what's left in the core, the remaining hot core would still be either a neutron star or a black hole. So here is an illustration or artist's impression of a supernova explosion. And this one, anyone knows which object this is? Looking familiar? No? Oh. Crab Nebula? Yes, yes, great one. If you simply just show me like out of nowhere, I wouldn't be able to tell. But yeah, it is the Crab Nebula. It is one of the most famous supernova remnant. So you see that all these filament is still glowing gas. It's very hot and tenuous and still persisting all the heat after the explosion. And somewhere in the middle, there should be a neutron star, even though it's like so tiny that we are not able to see. So these supernova explosions can actually have a very deep impact on the host galaxy themselves. So once a star explodes, all the heavy elements that was once produced inside its core gets released into the interstellar space. And those heavy elements can be later picked up by the next generation of stars. And then the next generations of stars would contain more content of heavy elements. And these supernova explosions can also have a lot of energy that drives a lot of gas outside of this, this galaxy. Maybe I'll try to turn this off to see. Okay. Everybody hears me okay still? All right, I'll just project my voice. So this picture actually shows, well, this is one of the pictures that I provided to Dan that he just showed you at the beginning of the talk. This is called the Cigar Galaxy, or M82. So this is also like one of the very like visually pleasant object for stargazing. However, you can see in this picture that there is like red colored gas coming out of the galactic plane. So basically we're looking at the galaxy edge on, like directly parallel to the plane. And this red colored gas is the outflow, the gas flow driven out by supernova explosions, and it's emitting X-ray. So it's super hot, it has a lot of energy, and M82 is not the only galaxy that shows this. So there can be a lot of galaxies once there's a lot of star formation activities happening. There are supernova explosions, and they just kicks out all this gas that contains heavy elements. And we can also call them, polluted gas or chemically enriched gas because of all the heavy elements in there. Aside from ejecting gas, galaxies can also obtain gas from the surrounding. So this is a simulated image of a galaxy at the center actually accreting streams of gas onto itself. And the gas comes from the intergalactic space, which is the space in between galaxies. So we're now talking about like way larger scales. This is one galaxy, and there might be like galaxies over here and over here. So the fresh gas typically contains mostly hydrogen and helium. It gets created onto the galaxy, and that can also be used to fuel future star formation. So now we have talked about how the gas may flow into the galaxy or outside from a galaxy. So if I were to give you, some random galactic plane like that, you're again looking parallel to the galactic plane, and I say, hey, can you please draw me some gas flows, inside or outside of this galaxy? How would you draw it? Based on the story that I was just introducing. Like this, and like this. Yeah, so that's great. So yes, there are outflows that typically goes pretty perpendicular to from the galactic plane. That is outflow. And the inflows, remember, they're kind of like coming through the filaments or the streams, and that are like more like closer to the galactic plane. And sometimes when the outflows are not traveling at a high enough speed, they're not able to completely escape the host galaxy. So they would fall back, and it's almost like a fountain. And this polluted gas gets reused or recycled. And of course, that's also where the next generation of stars would pick up. So there's outflows going outwards, there's inflow going in, and there's also, this galactic fountain kind of recycling everything. So the topic of this talk is called Do Galaxies Breathe Too? So first, I wanted to take a moment to actually talk about how humans breathe. So when we're breathing in fresh air that has a higher content of oxygen and lower content in carbon dioxide, right? And then, of course, it goes through our body through metabolism, And then when we're breathing out, it's more polluted gas that has higher content of carbon dioxide and also with a bunch of other metabolic waste, right? So for galaxies, if you think about it this way, it kind of also breathes that way. So it takes in the fresh gas that's mainly hydrogen and helium, and then it breathes out this outflow that contains more heavy elements. But then the problem here is, what is metabolism for galaxies?
Stars dying.
Oh, great guess. Yes. So stars dying and also forming, so that there's a cycle. Yes. So star formation or star forming activities, that is the metabolism in the galaxies. So once a galaxy takes in all this cold and fresh gas, it triggers a star formation. And then depending on the initial mass of the star, it would go through different tracks of evolution. But ultimately, the most massive ones, it explodes and drives all the heavy elements outside of this galaxy, and that creates the polluted exhale. And there's another reason why I kind of make this analogy between metabolism and also star formation activities. So for a human, once the metabolism stops, we're just considered dead, right? There's like no more life happening. And that's kind of the same for galaxies too. So for a starburst galaxy where star formation activities is like really active there, we consider those galaxies as like bursty galaxies, right? Pretty much alive and active. But when there's a galaxy like an elliptical galaxy that only feels very few stars, we consider that as dying, if not completely dead, unless at a later time it's able to accrete fresh gas from somewhere else, from the intergalactic space, that revive this galaxy by re-triggering the star formation activities in there. So sometimes I kind of wish that humans also work that way, right? That you just, breathe and you're like reappeared in the world. But sadly, humans don't work that way. But at least for galaxies, sometimes it could happen. And especially when galaxies live in an environment where there are also galaxies nearby, there could be gas interactions or exchange that revive their star-forming activities. So normally, when I give talks or I simply just talk about astronomy, I kind of agree that astronomy is a discipline that is mainly curiosity-based and has not a lot of everyday life applications. So that I agree. However, tonight I would like to take a different perspective and actually take a moment to appreciate the death of all the massive stars in the universe. Because if you think about it, when the universe was first formed, there was only hydrogen and helium created shortly after the Big Bang, when it was so very hot and dense and pretty much, it's just a plasma soup everywhere. However, now look around, we'll find all different kinds of things. So we have, chairs and tables that are made of wood and metal, and essentially it's like carbon and iron. And on a sunny day, we may go hiking or we may go to the beaches and we see the rocks, and that's made of silicon. Or even just all of us, we are humans, and we basically live on those essential building blocks that are carbon and nitrogen and oxygen, and also all the other key nutrients. So every single atom of those heavy elements was once inside of a star. And it was just through its death that it got released into the interstellar space. Later on being picked up by the sun, by the solar system, and when Earth was forming, it picked those up, and eventually life became possible because of those heavy elements. So essentially we're all just stardust at this point, and without any of those splendid death of massive stars, we wouldn't even be here. So this is kind of the inspirational moment that I always like to give. And if this was a 20-minute talk, I would pretty much just end here. However, I know some of you would be skeptical, saying, great story, but how do you actually study the gas flows, right? I mean, you showed us this big picture, but like what properties do you actually study, and like what's the questions, right? So the next little bit, I am going to just like use a couple of examples to show how we actually get data and do some quantitative analysis of these gas flows. So beyond just the conceptual ideas. And as I mentioned before, there's a term called the circumgalactic medium, or CGM for short. So this is the gas that is at the outskirt of a galaxy. And when I say outskirt, that is also a very vague definition. So here, if we're talking about a galaxy that's about Milky Way size, then we have the size to be about 25 kiloparsecs, which is about 100,000 light years. So that's a typical galaxy size. And then if you're looking at this halo of gas that's defined as CGM, you see that it's like about 10 times larger in radius or in diameter. So this is like how big of this gaseous halo that we're talking about. And of course, beyond that, we kind of vaguely define that as the intergalactic medium. But hey, in astronomy, everything's very vague, right? So if you ask me, okay, where is the boundary between the CGM and the intergalactic medium? Like, I don't know, sorry, but roughly there. So just pointing. So this is the idea of the CGM. And when CGM is being studied, a lot of times it's not only through the visible light. So for example, here we see kind of like two galaxies in the visible band, right? And they're just like hanging out in there pretty close. But if we're actually studying the gas, you can see these two, their gas is exchanging, and there's actually underlying activities going on there. So these are two interacting galaxies, even though we're not able to see that simply from visible light. So the tool that we typically use to study a bunch of properties of this kind of gas is called spectroscopy, or the use of spectra. And here I am introducing the three, I think it's the only three types of spectra that we typically use. So if we're directly looking at hot opaque light source, for example, incandescent light bulb, or a star, for example, including our sun, then what it gives out is a continuum spectrum, which says, okay, I am emitting light at all different colors or all different wavelengths. Right? So even though the intensity or relative brightness of those light might be different, but I'm giving you something at every single color. However, if there is an intervening cloud that you're seeing in front of the hot source, so basically we're looking right here, and through the cloud we're looking at this, this light source, then what we're seeing is an absorption spectrum. So compared to the continuum spectrum, which you can still see at the background, there are some dark bands that you also see. And those dark bands are where light is being absorbed, and that's why there's like less light that you get here. So in this plot, where you're actually plotting the relative brightness at the different colors or different wavelengths, all those dark bands would become little dips just because there's less light being emitted. And if you're directly looking at this gas that is now being heated up by the light source, so we're not looking right here, we're now looking directly at the gas right here, then what you'll observe is it only emits at certain colors or certain wavelengths, and the rest is just black. It's all dark. So, and this spectrum you see is like there are only several blips or peaks where light is actually being emitted, and for the rest, there's just nothing. So, okay, these can be kind of confusing, but as I am unfolding the story, you will see where everything connects. So if we're actually looking at the spectrum of some elements, you might be able to see, okay, so here I am showing the absorption and emission spectrum of 4 different kinds of elements, right? And let's just take sodium, for example. So what you'll see is the absorption bands or absorption lines on the top row, it perfectly aligns with the emission line in the emission spectrum, right? So everything perfectly aligns, and that's also for all these different elements. And this is because all these spectral lines, either it's emission or absorption, it's set by the unique atomic structure of that element. So for each element, it has a unique set of lines. And once, for example, I am just like taking data, and all of a sudden I saw, okay, there's a line around 500 nanometer. And then I know, okay, well then there must be sodium in whatever I am looking at. So these lines are serving as fingerprints of all these elements and help us trace, without going to the galaxy and scoop something and bring them back, to tell, okay, what is exactly there chemically. And of course, we all wish data could just be, that clean, and we can do something, like more qualitatively. But in reality, we're not only looking at, absorption or emission spectra like this, because it's very hard for you to quantify things out of these two. So what we do is we actually plot, again, relative brightness against wavelengths or colors. So for example, this is an emission spectrum of helium. And what you see here is the strongest line is this yellow line right here. And because it's the strongest, so it has the highest brightness among all these lines. So I am plotting it as the highest peak. And then there are a bunch of relatively strong, but not the strongest lines here in red. So I am plotting them as kind of strong peaks, but not as high as this yellow line. So basically what you see here is whenever you have a strong emission, of course in the y-axis you just have a peak like that. And it's the same when you're having absorption, and the stronger the absorption is, the deeper the dip you'll see. Okay, so now let's look at some real spectrum. And this is actually, I shouldn't say this is a galaxy spectrum, but this is an average galaxy spectrum that I created in my PhD work after combining hundreds of galaxies with similar properties. So this is kind of like an average galaxy spectrum. And just a reminder that when we're talking about a spectrum of a galaxy, it's way more complicated than simply just looking at, say, oh, it's a helium or sodium spectrum, because it's a sum of the light emitted by stars and gas. And they may all have different chemical compositions, right? So you're looking at this sum that contains so much information that you're trying to, disentangle in a way. And in this galaxy spectrum, what you see is, okay, well, it has some kind of continuum because it's not zero, right? So there's some kind of background light that's emitted by stars. And you also see these dips that are absorption lines from the gas, from the interstellar or circumgalactic medium that we're looking at. And there's also this emission feature that comes from hydrogen. So there's all different kinds of continuum, emission, and absorption when we're looking at a galaxy spectrum. So now, what can we actually get? What information can we get from just simply looking at these galaxy spectra? So one thing we can know is how the gas moves, or the kinematics of the gas. And that is, again, as a reminder, it requires us to essentially be looking at this circumgalactic gas right here as we are looking into this galaxy. So the galaxy contains stars. That's almost the background light source. And then it's surrounded by this gaseous halo that serves as this gas cloud. And essentially, we're studying all these dips or absorption lines that tells us about this intervening gas. So one thing we could know or derive information from is from Doppler effect. So Doppler effect states, okay, if a light source or a sound source is moving, then the frequency we receive is somewhat different from the frequency that it actually emits, right? So if a light source, a sound source is traveling towards us, then the frequency gets higher, and this is also when, when we're hearing, say, like cars honking as they're driving past through us, the frequency changes, the pitch changes. And this is the same with all these traveling gas. So when the gas is outflowing, and it happens to be that we're directly looking at the outflowing gas like this, right? So the gas is outflowing from the galaxy, but it's traveling to you. The absorption would actually be blue shifted because the wavelength gets shorter and the frequency gets higher. So if we already know for a certain element that the unique set of lines are at these places, then for outflowing gas, then all these lines are unanimously also being blue shifted, meaning that they're shifted to the bluer end that has shorter wavelengths. So the actual observed wavelengths is shorter than what they're supposed to be, or like what they're being measured in the lab. And this is what we see as, those gas must be outflowing. And of course, the faster the gas is flowing outside of the galaxy, the faster it's traveling to us, then the larger the shift is. So we can actually calculate how fast the gas is traveling through Doppler shift. So here is also another real spectra of galaxies, and don't be overwhelmed by all this labeling. I'll explain later. But what you can see here is so all these are absorption lines, as we were talking about, right? All these dips. So the dotted blue line, as you can see, that marks where the lines are supposed to be. That's where we are supposed to find them if the gas is not flowing at all. And you can see all these dips, the lines, they are unanimous, collectively all shifted to the left a little bit, right? And the left is shorter wavelengths, and that means it is blue shifted. And all these lines are showing blue shifted signatures, meaning that all these gas is outflowing. So this is one solid evidence of what we're seeing in galaxy outflows. And of course, you may also recognize some of the elements in here. For example, there's iron, there's magnesium, and there's also carbon, right? So by identifying all these lines, because we already have the unique fingerprints, we can also tell, okay, all these lines, they represent the chemical elements in the outflows. So now we know how fast they're traveling. We also know what makes up this gas. So sometimes I wish, research is just that easy and we're done, right? We're done. Hey, publish and question solved. However, there are other very complicated things that I'm not going to go into depth. But one thing I wanted to point out is, aside from the elements like iron, magnesium, you may also see the notation that there's two, there's one, there's two, and two, right? So those are also kind of confusing. And this is another very confusing area that, again, I think it took me 3 years in grad school to finally get used to this kind of notation. And that basically denotates the ionization state of this element. So the ionization state basically tells you how many electrons does an atom miss on the outside. So for a carbon atom, it's supposed to be having 6 electrons outside, right? So that is electrically neutral. So the notation would be if something is neutral, not missing any electrons, then we give it 1. I have no idea why it's not 0, because that makes more sense, but 1 is neutral. And if it's missing 1 electron, we call it singly ionized, and the notation becomes 2. So this one we would pronounce that as like C2 or carbon 2, but that's singly ionized. And of course, if it's missing 2 electrons, it becomes carbon 3, and so on. So why does this even matter? There are 2 things. One is the unique set of lines for neutral carbon is different from the unique set of lines of like carbon 2. So whenever you're identifying those lines, you identify not only the chemical elements, but also associated with its ionization state. And also you can imagine that in general, it requires more energy to strip off more electrons, right, from a single atom. So typically, the higher ionization state an element is, typically, and generally, it signals that it's a higher temperature environment. So it can kind of tell you a little bit about what kind of physical environment this element is living in. So if now we're looking at, now applying what we have just learned into this very complicated simulation maps. So what we're looking at, again, this is not observed data. This is when we're putting together a model and try to run these simulations. And you can see here H1, that is neutral hydrogen, which is just hydrogen atoms, right? And then we have silicon 2, carbon 2. Those are singly ionized silicon and carbon. And we have triply ionized carbon and silicon. And finally, we have oxygen that has lost 5 electrons, which is like really high ionization state. So what we see from these maps, again, this is just like both X and Y, it's just a spatial scale. What we see is it probes the atomic hydrogen atoms that's mainly along the galactic plane, right? Again, we're just looking at the plane like in parallel. And when we're talking about outflows from these low ionization species, it's kind of just like perpendicular to the plane, right? As what we were talking about. And it's also the same kind of for silicon 4, which is considered as intermediate ionization state. But for carbon 4, you see that it gets more extended in spatial scale. And for oxygen 6 is like a lot bigger, right? And all these are outflowing gas, but because they have different ionization states, they also occupy different spatial scales. And this is what makes outflows very complicated, and that's because it's actually multi-phase. It has all different phases, and I wish I could have an answer when you come to me saying, hey, how fast is that gas outflowing from this certain galaxy? I wish I had an answer for that, but in reality, I don't, because we have to talk about which kind of gas and trace by which kind of element. So in general, there are like 3 different categories. The cool phase, normally we talk about the hydrogen items, the neutral hydrogen, or the low ionization species, like the singly ionized species. So they're more localized, they're smaller in spatial scale, and they also travel at lower speed. So lower speed, when we're talking about, in astronomical terms, it's about 200 kilometers per second. So that's like 120, 130 miles per second. Still, not allowed, when driving, but that is like lower speed. And if we're looking at the other side of the spectrum, for the hot phase, then we have the highest ionization species like oxygen 6, neon 5, nitrogen 5, and neon 8. So they're almost like having very few, only maybe 1 or 2 electrons left, because they just live in very hot environments. And they are spatially more extended, and they're also traveling at much faster speed. And those can be up to 1,000 kilometers per second or like 600 miles per second. So it's just, like beyond imagination. right? And of course, again, as I said before, astronomy is very big. So we have an intermediate phase, which is called warm, right? So everything that's either not cool or hot is warm. So that's like intermediate ionization, including silicon-4, carbon-3, carbon-4. So things that kind of behave in between. So the last thing I wanted to talk about these like multi-phase outflows is, even though they're very hard to model because, as you see, there's just so many different ways to probe or study them, it's almost impossible to simulate them correctly when we're building our models, because if you tune this parameter right, you get the other thing wrong. However, this opens tons of windows for observational work, right? Because we just have endless things to study. We have endless species and endless topics. So one thing that really sets these, the phases apart is the hot phase is really substantially hot. And this is a plot when we're looking at it. So it's the, we don't even need to look at the y-axis. The x-axis is essentially temperature, and this is in log scale. So when things are centered around 4, that means it's 10,000 degrees Kelvin. So that's already really hot. And you can see all these 5 profiles are kind of like all around this same regime, 10,000 degrees. And that includes the neutral hydrogen and the carbon-3, carbon-4, magnesium-2, all the low ions or intermediate ions, they're all around here in this cluster. However, when we're looking at much higher or much hotter phases, we see nitrogen-5, oxygen-6, neon-8. Those are the 3 right here. So they really separate themselves in terms of temperature. And again, these are in log scale, which means these phases could be up to 20 to 300 times hotter than what we consider the cool phase is, which is already 10,000 degrees. So this is partially like what we know currently about these outflows. So I would say I enjoy doing the research a lot, even though I now have pivoted myself into something else. And now I am just going to very quickly go to this part, which is now I have introduced what I do for research, and of course that was something I really enjoyed doing in grad school. But that was not the only thing I did in grad school. So in grad school, I also got introduced to outreach, which is basically teaching astronomy and science, but outside of classrooms. And the initial opportunity came to me was when I believe I was a first-year graduate student, and I was asked to do a presentation in both Mandarin and English at an elementary school. So the request was very specific, and of course, in a small department, there weren't that many like bilingual speakers or volunteers they could find. So I was like, yeah, okay, it's just an hour, and I think I can remember all those planets' names, so I'll go. So I did, but that one I still remember. I just connected with the students so well. I could see their eyes lit up with excitement, even though they have probably already known all the planets and stuff. But that was the moment when I realized, I really enjoy this kind of human connection beyond doing this, very objective scientific research. So after being an experienced volunteer, I also pivoted myself to start leading the graduate student-run program at UCLA in the Astro department. So we visited schools with hands-on demos. We organized annual science fairs called Exploring the Universe, which is still ongoing. And there was also the solar eclipse back in 2017, which feels almost like 1,000 years ago. But yeah, we had a partial, and we were not prepared for 4,000 people showing up. We only had like 5 telescopes, so that was a big mistake. And talking about an experienced event planner at that point. So learning from experience. So when I was trying to graduate from my PhD, there's really this, to me, almost like life-determining decision that I had to make, because I find myself really enjoying doing outreach, but do I want to continue with research? Do I want to do maybe teaching, or like where things are going? So based on what I sort of envision, I was like, okay, well, I could keep doing research for a little bit longer, but I don't envision myself doing that for the rest of my life. So perhaps not getting a postdoc research position. I love teaching, and I have taught as an instructor also at UCLA, like to other undergrads. But I also kind of like don't see myself doing that for the rest of my life. However, UCLA, the astro department was very kind. So they knew that I was like trying to apply for jobs, and I didn't get any offers even when I defended. So they're like, hey, you're more than welcome to stay as a temporary lecturer until you get a full-time position. So that was a very tempting offer. And I said, thank you, yes, because I don't know how long I'll just stay here until I actually get a job. And then there is another opportunity that came along. That was at UC Riverside. So the professor was actually not looking for an outreach person. When I approached him, he said, oh, I have money, but I don't need an outreach person because I already have one. However, what about you do half research and half program management? And I said, what about outreach? Can I also do outreach? He's like, yeah, you can volunteer your time to do outreach. So I'm like, okay, fine. Yeah, even though that is a new environment, it seems like a new path. But I knew, okay, well, for the UCLA position, it's probably very hard for me to have the time and energy to do outreach even beyond teaching. But at least at UC Riverside, I can still try to find my path. And that's why I transitioned there, even though there's still a research component, which I'm very glad that I continued engaging in. So at Riverside, well, funny story is, after 4 months that I had the conversation with my PI, with my supervisor, and he said, oh yeah, I already have an outreach person, I don't need you. The outreach person left. So I came up to him saying, hey, can I now be the outreach person? And he's like, no, but you can do it for free. Because I still need someone to manage the programs. I said, okay, yeah, that's fine. And I'm really glad that I still had all these programs, because that's where it really helped me sort of like do program management that essentially also like benefit when I'm doing outreach. So at UC Riverside, there were high school programs that was NASA funded to support high school students from underrepresented minority groups to pursue college education and STEM careers. And this was like one of the science nights that we UCR run for them, led by me. And this was a subset of us volunteering there. This is a handmade banner that says PHS welcomes UCR Science Night 2019. PHS is one of the most underserved high schools there, Patriot High School. And it's still, looking at this picture now, it still melts my heart. And it's really this kind of connection and impact that I feel that I'm making that really drives me to continue with education. There are many talented researchers that I think can do a better job in research, but this is where I feel I can uniquely contribute. And of course, there are also different kinds of programs at UCR before COVID. So if you note, almost all of these are in 2019. So either the 50th anniversary of moon landing or the Mercury transit. And also like high school science nights and classroom visits. In 2019, so things were going really well until, boom, COVID. And COVID was, of course, a pretty hard time because it was just like very hard to keep everything together and also keep your audience engaged. However, we were able to I was able to, spearhead and try to partner with the local astronomical societies, and we were doing like monthly virtual stargazing with storytelling and also like actually live capturing images. And there were, of course, also public lectures and even K-12 camp sessions that were all adapted to a virtual option. And now at KaiPac, I continue to do all this kind of educational programs, which include, again, public lectures that is offered in hybrid format. And we have a stargazing night at the Stanford Student Observatory, also with 2 domes and 2 large telescopes with a bunch of portable telescopes. We have a virtual summer camp for high school girls, which is completely free, and where high school girls learn computer programming, astrophysics, and quantum physics. And we also have a program in Spanish called Noches Astronómicas. And probably from my pronunciation, you can tell that I do not speak Spanish, but I help run these programs with a bunch of enthusiastic Spanish-speaking scientists. And of course, there are also large-scale events, including the 2023 solar eclipse and also the astronomy fair, which we're going to offer again in 2025. And I have another slide for that later on. And aside from that, I am also engaged in training students, including summer interns from different universities and including community colleges to do summer research at Stanford and SLAC. And there's also, we have a post-baccalaureate fellowship that's for recent college graduate to do a paid 1-year research fellowship at KaiPac. To help them get into competitive graduate programs. And there are also Stanford Pi program that we offer for local undergrads, especially early undergrads from community colleges and 4-year universities to help them navigate academia and also STEM fields. So I'm going to skip this too. And basically, if I were to share anything now, 6 years after I got my PhD, if I'm looking back and saying something to maybe the high school self, I would just feel at all the intersections where I felt, okay, this decision is so big that I better not mess up. I mean, now looking at it, maybe the impact would have not been that big. As long as I have like a vision and know what I want to do and what I don't want to do, I think the general direction is set. And even though I take different paths, probably they'll eventually lead me to, in general, the same direction. So if you're like a high school student or college student trying to figure out, okay, well, I don't really know what I want to do yet, and that's totally okay. I mean, follow something that you're interested in, doing something that you would not regret spending maybe 4 or 6 years studying. That would be the first advice that I have for you. And also, now it's like I still consider myself as young and exploratory. So just try different things. I mean, I tried that like physics and math heavy research project, and I know what I didn't want to do for sure. And that, by the way, that's particle physics. So, never again. Yeah. So, and if you want to stay close to STEM, there are so many different ways. There's not always just this linear path where you're an undergrad, you grad, become a postdoc, and eventually a professor. I mean, that is one path. But if you want to stay close to science, there are so many different things that you can, work on writing about science. You can teach science. You can be in industry applying science to actually benefit our everyday life. You can make policies that really advance science, or you could, become a science administrator to sort of like give out funding to really support what is mostly needed. So I will probably leave it here as the last slide. if there are any interest in participating in the KaiPAC events, we have public lectures, again, as I mentioned, in hybrid. So you can simply just watch them on your couch. And we also have online chat moderators to answer all the questions that you have as they come in. And the next one we have is actually following the end of the heliophysics big year. We're going to talk about the aurorae that we hopefully recently caught, and also the solar maximum, what really drives us to see this blooming numbers of sunspots and aurora and solar storms. There's also a Stanford an astronomy fair that we're organizing on the Stanford campus, April the 19th. Mark your calendar. There will be more than 30 different kinds of booths, not only astronomy, but all related fields in STEM, featuring hands-on demonstrations, live experiments, and also a series of mini science lectures. And of course, there's the summer program for high school girls, and also Spanish outreach program that I already mentioned. So if you want to follow or simply just get monthly notifications of upcoming events, here is our QR code. And this is my email. And of course, if you want to ask any questions, or if we could partner up for something that serves you or your classroom or your students, I'm here. I'm here to talk, and I love collaboration. So I'll probably leave things here. Thank you.